density dependent on the symmetry energy in the laboratory. This is the outline. I will just remind you first the basic definitions. Then I will describe quickly the energy density functional. Its basic point is due mainly to the famous theorem of Walter Kuhn, that for each many-body system with a two-body interaction, there exists a functional. If you can guess it right and minimize the functional, you get the energy. This type of approach is now currently is used heavily by chemists, and they've developed very sophisticated computer program because they are interested to find out how the atoms are organized in a molecule and use it for drugs. Then I will describe the method we've been using to fix the energy density functional, starting from the Scherm interaction. The Scherm interaction has been developed already due to Scherm in 1958, and then Brinkenhoff in the 70s, pushed it to a higher level of using it to calculate properties of nuclei. In the meantime, there are more than 250 Scherm interactions, and the main reason for this diversity is that the number of data points that are used to fit the parameters are not rich enough to determine all the parameters. So therefore, in the approach I'm using, I'm including specific type of nuclei, trying to separate the correlation between Coulomb energy, spin effects, and symmetry energy, and additional conditions on the energy density functional. Then I move to the issue of the measurement of hot nuclei. If we start from two-body interaction, one can calculate the binding energy per nucleon as a function of density. This is what is called the equation of state. One gets a curve that looks this shape. On this curve, we know very well that this is the minimum binding energy per nucleon 16 MeV and density 0.16. In order to extend our knowledge of the equation of states, we need the second derivative. The first derivative is 0. And the second derivative is directly related to the compressibility coefficient. So we have a very simple expression for the energy density for the equation of state. I just should add that in this curve, this region is not correct because this is obtained assuming that the many-body system is all the time made of nucleons. At low density, we have clusterization, and therefore the curve should really go to minus 80 MeV or so. The main data that fix the compressibility is well known is the compression mode in nuclei. And there are two compression modes that we have data on. It's the monopole and the isoscalar dipole. Okay. The monopole is just a breathing mode. It's isoscalar, the neutrons are moving together. The dipole is missing, because it is not the first tone. The first dipole is the center of mass motion, which is spurious. Therefore, the actual the isoscalar dipole we are talking about is the overtone, which will be corresponding to the overtone of the monopole. And just, again, a compression mode with an helical bond shape. There is a lot, in the recent years, there's a lot of interest to improve the energy density functional in nuclei. There are new data since the time of the 70s of say, with Brinkerhoff and company. And that's what I'm going to describe. And the reason is, okay. For a reminder, the scheme interaction is a delta function interaction, all the terms, and has 10 parameters, the Ti, the Xi, alpha, which is the exponent of the approximated three-body terms, and the strength of the spin orbit. And if we try to calculate the expectation value of the Hamiltonian, we get the energy density functional. At this point, one can forget about the scheme interaction and just take any ansatz for the energy density functional. Minimizing the energy density functional, we derive the Hartree-Fock equation. We do the calculation in the Hartree-Fock equation for certain quantity, compare with data, and make this square thing. I'm not using this method of least squares fit. What I'm using is the SAM method, which is simulating an method. There are two elements in the fit that I'm doing. Is first, if you take all the scheme interactions and try to see any irregularities in the parameters, they are everywhere. Okay? Therefore, instead of trying to vary the parameters of the scheme interaction, we determine certain nuclear matter quantities that we have a good idea how much, what's their value. For example, the binding energy per nucleon, I should expect it to be between 15 MeV to 17 MeV, the compressibility between 200 to 300, the saturation density, and so on. Each quantity can be written in terms of the scheme parameters. So if I have these 10 quantities, the effective mass, the surface energy, the symmetry energy, derivative symmetry energy, kappa is the enhancement factor of the isovector dipole, G0 prime is a parameter that controls the spin, isospin excitation nuclei, and the spin orbit. If I know these values, I invert the relation and I have the scheme interaction. Therefore, in the variation, what we play with as parameters are the nuclear matter quantity. So we start with a certain quantities, and we have two vectors. V0 is the vector in which all the minimum values for these quantities. V1 is the vector with all the maximum value, and we vary the values of this quantity between this region with a certain step. So we start from the initial value, we do the Hartree-Fock, we find the chi-square. Then we use the random parameters to decide which one I want to change. Let's say I change the m star, use another random parameter to decide by how much. The moment I change m star, I have a new vector, and the m star is related to several of the scale parameters. Then, of course, if the new chi-square is smaller, we take this value of the parameter. If not, we still decide whether to take it or not. This is called the Metropolis method. We take an effective temperature and another random parameter with 0 and 1. So if this is still larger than beta, we take the new set of parameters. This is critical to prevent us from falling into a local minimum. So the whole idea of the SAM, of the simulated annealing method, has analogy in cooling a liquid very slowly to get it into the lowest energy. However, there is no theorem that tells you that you eventually will get into the global minimum. So we start from a certain effective temperature, we repeat the process many, many times until we are satisfied with certain convergence. Then we reduce the temperature. K here is an integer, 2, 3, 4, and so on, until we reach a minimum. In all the cases we did a least square after that, and there was no change. Now, the other element of the peak is the data. All in a bold phase is relatively new. Pay attention that we have the nickel 48, which has 8 extra protons, And it is very, very important to decouple the Coulomb contribution from the symmetry energy. Most of the fit with nuclei are always those with n larger than c, and there is a strong correlation between the Coulomb contribution and symmetry. So it helps a lot. We have also very neutron-rich nuclei. Now comes to the single particle spin orbit. Hartree-Fock is not supposed to fit the experimental data of single particle state because it doesn't contain the frequency-dependent effective mass. So, therefore, we look at data in copper 57, nickel 57. If you look at the splitting, is about 1 MeV. Standard spin orbit a la Bohr model zone will not reproduce it. It's too small. So we carried out a particle phonon coupling model to extract the bare single particle energy. And the splitting went into this value of 1.8, so we use that in order to determine this, to fix the strength of the spin orbit. We don't use any value of Rn minus Rp in lead or whatever, because in my opinion, it's still not known, and I'll come to that again. However, there is a very data that many people forgot, is the RMS value of the last orbit in oxygen 17, which is the 1d5 neutron distribution, and the F7 half. This was done by electron scattering and 180 degrees. This is magnetic scattering. This is the highest L. Therefore, you actually scatter from a spin on the wave function of the neutron. And why it is forgotten? Because the value of this are a little bit smaller than what you get from Hartree-Fock. For example, if you pick the mass of the charge radius of calcium-40, you will get this to be 4.2 and not 3.99. By the way, O'Neill interaction is very close because we had a discussion while the interaction was good. Again, as for the first time, we include the breathing mode energies of several nuclei into the fit. We don't just fix the compressibility, we have the values of the monopole energy in the fit. So if there is any isospin dependence in the result, it will affect the fit. This is not all. We include many other conditions. First, the 12 stability conditions of Landau, the parameters F0, F1, F1, F0 prime, F1 prime. And the reason is to make sure that the energy density functional that I get will be stable under small oscillation. Example, the compressibility depends on F0 and F1. If F0 is less than -1, the compressibility will be negative. So we ensure that all these quantities, the 12, 8 for a symmetric system and 4 for neutron pure system, will be larger than -2L+1. Up to density between twice the saturation density and 3 times the saturation density. Second, G0 prime with many interaction is negative and small and create problems in the spin isospin excitation. And third, that the derivative, the slope of the symmetry energy around 3 times the density is still positive. This is what the requirement of colleagues from neutron star calculation to get the Urta process going, right? And we don't take, at the moment, the isovector dipole into account directly, but we make sure that the kappa, the enhancement factor, is in the right side. So we have this fit to nuclear method, and it is an example of the interaction. K0, we have several additional. And let me go, after we have the energy density functional, we carry out self-consistent Hartree-Fock RPA calculations. This is a table which shows results from the relativistic model of NS3. The author is here, Peter Ring, and they got a compressibility of 270. This is the SG2, the Sagawa interaction, and this is the interaction we produce. The first point I want to pay attention they seem to fit data reasonably, that the compressibility is changing, but also the symmetry energy changing. So we were able to create a stem type of interaction with also high compressibility and high symmetry energy that reproduce practically the result of NL3, which means there is no dependence on this, in the structure of the energy density functional between relativistic model and non-relativistic. So the problem that maybe the compressibility extracted is model dependent is not there. Second, the same problem here. If you see the calculation with Sagawa interaction originally were not self-consistent, and the values that were obtained were 14.4 and led to statement that the compressibility from the monopole should be below 200, whereas the new interaction and 230. If you take self-consistency into account, there is no problem, and all the models agree with 230 MeV compressibility plus minus, I would say, 20, and this plus minus 20 depends what symmetry energy value coefficient you want to take. However, not everything is well in this area. There are new results of measurement of the isoscalar resonances in calcium-48 that were done recently at Texas A&M, monopole, isoscalar dipole, and quadrupole. And one of the interesting results is that the position, the centroid of the monopole in calcium-48 is higher than that in the calcium-40. In the semi-classical models, you would expect a decay in the energy around 8 to the 1/3 or so. So the first thing we did, we tried many different interactions, and you can see that they are the calculation a little bit above the calcium-40. Many of them are well in the region of the calcium-48, but if you take the difference, all of them are below the experimental data. And this is an issue that we are investigating now to see if this can tell us another condition of limits on the energy density functional. However, if you look at the literature, there are many publication review articles and so on. If you take the numbers there, you will see no problem. You can have interactions that give you a difference of about 1 MeV. But these calculations that were published are not fully self-consistent. So this is a check that if you don't do fully self-consistent calculation, you will not get the correct result. Well, another point that we did, we tried to carry out to understand what's really going with all the interaction and maybe improve it. We carry out correlation checks with quantities that people use in the literature. Especially for the symmetry energy, the symmetry energy, the value 8.1 of the Fermi -3, the derivative of the symmetry energy, and so on. And we don't, if you look at the difference between calcium and calcium-48, there's a lot of statement that you measure the position at the rich neutron, you will get information about the symmetry energy. Even though this difference in terms of the n minus z over a is the largest we have. It's larger than what you expect in an NT, but we don't. And we don't see much large correlation coefficient. And the correlation with M star is actually correlated with the fact that the interaction have there is a correlation between the compressibility and the effective mass. So it's not separate. You see strong correlation of the L equal 2 and so on with effective mass, and all this are not really necessarily new, but just remind. So this is another direction we are doing. I have similar thing for the isovector dipole. In calcium-40 and calcium-48, we don't really see much strong correlation with all these quantities. The point that I want to emphasize very strongly, and this is related to the next point, is the following. You can start from a certain interaction, vary some parameters to change the symmetry energy. And then you calculate the isovector dipole and you see some correlation. And you claim that the isovector dipole determines that. But the moment you change the interactions, the new interaction that you have did not fit the experimental data. Well, the interaction I'm using, all of them fit the experimental data. So one should be very careful in this conclusion. Here is another result, very recently showed up in the literature, that if you measure the isovector polarizability, which is related to m-1, which is the integral of 1 over E times the strength function, then you can pinpoint the value of Rn minus Rp in nuclei. The experimental paper in this revelator used the result that was produced in the literature, theoretical one, in which the Skerm interaction produced by Reinhardt was varied, and they got a very, very small ellipsoid, and then determined that Rn minus Rp in late 208 is about 0.17, plus minus 0.02. I look at the number, the plus minus 0.02 is smaller than the error we know about the charge radius.
We don't know the charge radius well enough.
That's right.
The charge radius is a factor of 10 worse.
No, it's about it's 0.5%.
I was in the experiment you were quoting.
Ah, you are there. Okay, good. Now, then we started with the graduate student. I took many classes, and until we push it. So the moment we were ready to send it to publication, there is another paper. And the other paper with Pikarevich and company collected results from all the practitioners on this, and they got similar figure that you have here. But then they did the following, which I ask you to judge. You see that there are several interactions that agree with the very good experimental data. You take an average, and you calculate sigma squared. Sigma is just a minus b divided by square root of 2, if you have a straight line. So you get the value of 0.17, again plus minus 0.02. In my opinion, this is not a proper conclusion, because this is theoretical calculations. All what we can really say, all the interactions in this region agree with data, which means the value could be 0.14 or 0.20.
Well, I think we should take this up right now.
Yeah, that's why I'm making this statement, because I want to react.
The thing is, I mean, they did this correlation analysis and calculated that correlation coefficient which you have there.
Sorry?
And for that 208, they did the analysis and calculated that correlation coefficient for the different. But then they did something else. They also correlated them to the tin isotope.
That's fine.
It just needs more data.
But my point, the statement in the paper that Rn minus Rp in late 2A is 0.17 plus 0.8 is false, in my humble opinion.
I disagree with you.
Well, I think, as far as I know, when you have an experimental value and you have several theories that agree with the experimental value, the correct statement to say is that all these theories seem to be in agreement with data. Not to take an average of prediction of theoretical values. Okay, let me, in 5 minutes, to summarize quickly what we know about nuclear matter. And what I will say is the following. The only data that we have about temperature and density dependent of symmetry energy comes from heavy ion experiment. In a heavy ion, you collide two heavy nuclei. You create a system compressed, hot, that expand, fragments. There is interaction between the fragments. The interaction leads to thermal equilibrium and chemical equilibrium. So you reach a certain size, a point that we call there is a freeze out. And now what you have there can be described in a statistical way, and you can calculate how many fragments you will see of lithium-6, lithium-7, and so on. And there are many, and the analysis of that is, it can go back to Zaha, of telling us why the stars have colors, in which you take ratio of yield of fragments, and if you take double ratio, you will get the temperature. So, what I want to emphasize, you see the density of the cluster S, which has A and Z, divided by the density of neutrons to the power of n, number of neutrons, density of the proton to the power of protons in the cluster is given in terms of the internal partition function and the binding energy of the cluster and correction of Coulomb. Now, if I take the yield of lithium-7 and lithium-6 and take a ratio, I will have a relationship that will include one neutron density and the difference between the binding energy. If I take another ratio, helium-4 and helium-3, I'll get the same thing. If I take the double ratio, I will have the double ratio directly related to the temperature. So we fix the temperature, we go back to a single ratio and get the density. There are many corrections to that, and one of the things I want to discuss is what's called the medium effect. When the nuclear matter expands and get into a very low density hot, we get clusterization. This is not in the mean field. There is a formulation how to deal with cluster in medium. Its binding energy changes with the density, decreases until it dissolves. So the question is, what's the relationship between the binding energy of the cluster, the density and temperature? One can start from the relationship between the density and the single particle spectral function, expand the spectral function in terms of get spectral function in terms of the mass operator, expand the mass operator in terms of cluster, and you get an effective equation for a cluster of A nucleons, which include also blocking factors inside the medium. This is relatively well known, and this is an example how the binding energy of a deuteron in nuclear matter changes with the density. The calculation is done for 10 MeV temperature. You can see that very, very low density, we get the minus 2.2, and then it decreases slowly, and you get here the mod point. There are differences between the curve because we assume that the cluster can be moving in the medium or not moving in the medium. Therefore, in the calculation of the temperature and so on, one should take into account that the binding energy of the nuclei changes if they are in the cluster form. In that, the effect of the medium on the binding energy of the cluster. This is the equation of state that I actually solve self-consistently to get the value. And let me discuss this curve. To get information about the symmetry energy, one uses what's called the isoscaling. You do reaction with a certain target, but two different nuclei. One rich with neutrons, one lack some neutrons. Temperature being about the same. If you take the ratio of the yield of a certain nucleus, you will get dependence on the difference between mu n and mu p, the